behavior you might see is this sort of mob behavior on the internet that, especially this concept of biggest group ever or similar logic, those sorts of things can actually be very damaging for products or for websites. Users can be fairly annoying, and one of the interesting ways to survive while scaling these websites is just to sort of cut users off sometimes. You have to always be willing to do that. And this biggest group ever logic is a great example of that, where you just don't let them do that. Once users create a biggest group ever logic, once it blips on your radar and you say, oh, wow, we have 10 million users and 10,000 of them have joined this group because it's called the biggest group ever. Maybe you should just kill it then before it gets to 100,000 or 200,000 and you annoy 10 or 20 times as many people by killing the group. And that also sort of sets up the expectations that that stuff isn't allowed to survive long term, so there's no point in starting it in the first place. Because I don't know if you've ever tried to scale a group-based system in a scalable system, where you have a single group with 200,000 users, and it isn't very fun. Everything else in your system may work fine and may handle all the typical cases and scale just fine, and then one user views the group page for the biggest group ever, and it can take down your entire system. Additionally, users may have vastly different usage patterns. So trying to classify sort of the average user is often fairly difficult. And you at least end up with a few different classes of users. And as you try to scale systems, particularly we'll talk about partitioning systems and such, the fact that users have different usage patterns is both something that makes it more difficult to scale and potentially something that you can leverage to make it easier to scale some parts of the system by, for instance, dividing users based on some sort of class. Some interesting behaviors in this whole Web 2.0-ish era. Web 2.0 to me basically means it's very easy to manipulate things database-wise. You move from this form-based systems of click, click, click to adding a note on Flickr. You just basically click one button and put the note where you want, that sort of stuff. The downside of that on the database side of things is that all of those little easy behaviors are often database interactions through usually AJAX calls or similar. But the key point is, you're clicking on a note. It isn't, even though you haven't reloaded a page and that's not reflected in maybe the hits of the website or something like that, you're actually affecting the database. You're, in most cases, writing to the database because you're doing things like adding tags, adding notes, highlighting things, whatever it may be. Those are painful things to scale. And of course, the downside of that is everyone expects you to have that stuff nowadays. So you can't just say, well, we don't do that because it's hard to scale. So you have to be able to live with it and make it work. If we look at a couple of the basic tenets of building scalable systems, I think there's a few main points, and this by far is not the end-all, be-all sort of list of things that you need to do. But in general, don't design scalable systems using components you don't have control over or that have loose tolerances. And DNS is a good example of both of those, for instance. That we'll talk about failover. We'll talk about high availability. DNS is pretty much right out. You can't use it for most of that stuff because it's sort of an ugly hack that's great for typing in google.com and going to Google. It's not so great for failing over mission-critical database traffic from one machine to another instantaneously. And try to avoid using processes. And by this, I don't mean daemons in the sense of processes, but just human processes with potentially ugly side effects. So things like having to change code or having to change a configuration file, which is basically code, in order to do a failover or to add a new server or to do something like that. That stuff should be, it's metadata, and the key word is data, which means it often belongs in some sort of database of some sort. And that often isn't a .php file somewhere. Another interesting one is just from practical experience, if a user doesn't think or notice that something is down, it's not really down. And you can take advantage of that in a number of ways. And you're expected to take advantage of that in a number of ways. First of all is that we'll talk about caching stuff. But if something is cached and the user gets it out of the cache, even though the database is down technically, they never noticed because it was served out of cache. And you can use that to survive some sort of very small outages. Additionally, you can think of that in the more global sense that if an outage affects only a small percentage of your users, most of your users don't think anything is wrong. So if they don't think or notice that it's down, it's not really down. So you may have an outage affecting 1% of your users, and that doesn't have, maybe it's a 5-second outage affecting 1% of your users. That doesn't have quite the same effect as a 5-second outage affecting all of your users. And you can count that in your uptime as well. You want to eliminate or limit single points of failure. And actually, to elaborate on that last point as well, there was a study not too long ago about uptime of like the top 10 major websites. And how they calculate uptime in that sense was obviously very interesting and probably largely incorrect. But the funny thing was that they sort of reported Yahoo as having 0 downtime. And I happen to have worked at Yahoo, but that doesn't really change anything. That that if you look at something as big as Yahoo, it didn't have 0 downtime. There's just no way that happened. But between a combination of how they're monitoring whether it's technically up and how many of those outages affected, maybe it was a particular user that they're counting as, or that's logging in to check that something is up or down, whatever the case may be. It didn't affect that particular test, so it didn't get counted. They didn't notice. I'd be interested actually to know exactly how they counted that, but nonetheless, you can look at that and say, yeah, Yahoo has 0 downtime. In reality, little pieces go down here and there. A user can't log in for 10 minutes. A user gets kicked out, things like that. But those don't affect things in the global sense. It's I don't even know that Yahoo has had an outage that affected every user for many, many years. I have no idea what the numbers on that would be, but it just doesn't happen. And the same thing goes for Google, and the same thing goes for nearly every major website. You don't have outages that affect everyone. You often have small outages that affect subsets of your users for different periods of time. You want to eliminate or at least limit your single points of failure. And one of the interesting things here is just sort of examine, if you have any single failure or one of anything in your system, try to determine why that is. It may not be financially sound or a good idea even to try to fix that, but to know what it is always a good idea. So come up with a list of what are our single points of failure and why are they single points of failure. And often that will just come down to single point of failure, core router, too expensive, or it could be a load balancer that a second load balancer that's equivalent would be another $40,000. So it's just too expensive and it's not worth it for the failure rates of that particular component. If you come down to a single point of failure, we have a single disk in this primary database machine. That's a really bad idea. Those things fail all the time, and that's an easy one to fix. You could say it costs a few $100s to fix it, and some administrative time to either re-image the machine or build a new RAID or whatever the case is. Coming up with that list allows you to easily go through them and classify how expensive is it to fix it in real money and in developer time and things like that. And you can go through that list sort of from the bottom up and fix the easy ones first. The last tenet is basically cache everything. And you have to be fairly intelligent on how you cache things. But in many cases, in any large production website, if you log in, if you're reading anything that's remotely popular or you're looking at anything that's remotely popular, it's likely being served out of a cache rather than directly out of a database. It lives primarily in a database, but you're seeing it out of a cache. And that comes down to a lot to access patterns on whatever product or whatever thing you're building. But in many cases, you'll have a small subset of things that are accessed far more frequently, and caches help dramatically in that. Trying to serve all of those out of a database directly is a bad move. Yeah?
So does that mean the cache machine fails less than the database machine?
Not necessarily. In general, so if you look at sort of a typical design, you may have some highly available MySQL system behind the scenes, and one or more, most likely more, memcache servers sitting in front of that. So the cache servers, well, I would say they probably do fail less. But even if they do fail, the worst case is that you send more traffic to the databases. They don't fail in a way that you lose data or that you lose traffic or that you lose whatever. They fail in that they don't have, they're down, or they don't have keys available, they don't have whatever, memcache isn't running, whatever the case is, they're not really breaking things effectively. They're just causing response times to be slower. The other interesting thing, though, is that things like a memcache server is effectively stateless. You don't have a large database to restore. If you lose a memcache server, you just need to fire up another memcache server listening on the right IP address, and it will automatically start to get populated. So you can easily do things like N+1 for memcache servers, where you have maybe you need 5 memcache servers to run in production, so you have 6 of them, and you have a spare one that you can start up for any of the other 5 that have failed. Whereas in a database architecture, you would often have N×2, so you have duplicates of everything, because they're stateful, and you're probably using something like replication or DRBD or anything else to get the data where you need it to be. You can't easily just start up a new MySQL daemon somewhere and have it just work. But a little bit of a digression, I guess. So I divided the lifetime of a scalable system into sort of human components of different stages of life for a human, and mapping them into different stages of life for a system, where a system is likely some sort of product or website or something. And we'll mostly focus on web-based things, because that's what most of you are likely to be building and dealing with. So although there are many different types of systems, we'll spend the most time talking about systems related to that. If you look at how things start out, typically, I call this the newborn stage. Basically, you've just created, it's beyond an idea, basically. It's no longer an idea, it's an implementation. But you haven't thought a lot about the future, basically. You've created the thing. You've probably done it with shared hosting because it's cheap. You've worried a little bit about query optimization, probably because your very first revision was really, really slow. So you hacked things a little bit, made some queries faster, added some indexes, but you didn't spend a whole lot of time on that. You don't have much control over the overall configuration because of the shared hosting or similar environment. The overall performance may be poor, but it doesn't really matter because no one's using it. But then the next stage is, people start using this thing, and all of a sudden you realize that performance is really, really bad. It's not scaling as well as you had hoped. You need to start finding and fixing bottlenecks. So the next stage is basically often you move from your shared hosting environment to a single server. So that'll give us, we're not fighting with others basically now for resources. We're just fighting with ourselves. But you still have maybe database and web server competing for resources. The database needs lots of memory for caching things. It needs I/O. It needs all kinds of things. That's probably not well suited on your single dedicated server that you probably got for $150 a month. But usually the first thing that you'll see will be, depending on how write-heavy your application is, of course, the first thing you'll probably see is just memory contention, that you can't have enough Apache processes running to handle the traffic you need to have without having some sort of conflict, either in principle or in actuality, with the database itself. The database needs all of your memory for caching things, and of course the web server needs variable amounts of memory depending on how much traffic it's serving and how complex your website is, how many modules you've loaded into Apache, basically. And you could be looking at a lot of memory. And no one has really fixed PHP to work in the multi-threaded Apache, so you lose big on that one as well. So the next stage then is likely that you split things up. So we've gone from shared hosting to our own server. We outgrew our own server, usually based on just process contention. And now we're to splitting things up, often to separate web servers, separate database servers. And at this stage, actually, it's very, very common just to split from, not from 1 machine to 2 machines, but from 1 machine to 3 or more. Because it's really easy to split the web server side of things. You just need to have the code in the right place on the web server, and it just sort of automatically works. But you stick with a single database server since that's a lot harder, and maybe you don't see the gains from doing so at that particular moment in time. So you get a single database server since it's hard. The next thing is, of course, since now we have maybe 4 web servers, now all these web servers need to keep state amongst each other. You probably, let's say you're using PHP, you might have been using file-based sessions or something like that. Now you need to store those in some central place. So often that's the database. So now you're adding more overhead in managing the overall system. That often that overhead ends up back in the database. So you end up with even more load in the database. And of course, now you've got the same overall traffic, the same overall everything, but you've added network overhead and you've added all that stuff. So the system is overall slightly less efficient, although you have more capacity. And that's an interesting trade-off that you often make. And this seems like a really minor one. And in fact, the site is probably faster, but it's actually technically less efficient. And oftentimes, you're trading efficiency for overall scalability. That we don't have to get 100% efficiency out of a system. In fact, in production, you would rarely get more than 50% efficiency out of a system. And that seems like it's a really, really bad thing. It seems we're wasting half the hardware then, right? Not really. If you're getting 100% out of every system, that means either you have a really, really, really good system in place for adding additional capacity exactly when necessary, which is highly unlikely, or your systems are just overtaxed and you need more hardware and more whatever, which is the much more likely case. So usually at this point, your single database server becomes your biggest bottleneck, either in reads or in writes. So our single database server now, it either doesn't have enough cache memory, or it doesn't have enough spare CPU to handle all the requests we're trying to send it, or it doesn't have enough spare I/O to handle writes we're trying to send it, depending on the type of application you're building. So the next step then is we need to get our database running on multiple machines. The easiest way to do that most people see is just move tables around. So we have all these tables that are sort of nice buckets of things, of data, that we can move. We can move this one table from one machine to another and move some of the load over there. And that works OK, except you still have single points of failure, which we'll come back to, since you now have actually many single points of failure. But now it's also much more difficult to deal with this in the application, because particularly if they're completely separate sets of data, let's say they were even in separate databases and they're not really related or coupled tightly to other parts of the system, it's fairly easy to move them to another place. And you just have to change a little bit of code so it knows where to access that data. But you end up with either individual tables or sets of tables that are so tightly coupled that you can't really split them up. So let's say the simple case, you just have a single table that got 90% of your traffic. Moving everything else off is only going to save you 10% off of that machine. So you still have this one big table with 90% of your traffic. What do you do then? Often, another simple thing you can do, you can use replication to move some simple things like reporting off of your production primary master database. That can help somewhat, depending on how heavy reporting processes are. You can use replication to help you scale reads if your application is very read heavy. As I mentioned in the beginning, in the sort of tenets and such, modern applications, these Web 2.0 applications, aren't often all that read heavy. It used to be the case that you would build a new application, like /dot being an OK example, where you have effectively one publisher and many, many readers. And actually, MySQL replication was created partly because of a sponsorship from /dot to add replication. But nonetheless, for an application like that, it's very, very read-heavy and somewhat write-heavy. You have lots of comments, but you don't necessarily care if the comment shows up immediately. If it shows up 3 seconds after you post it, big deal. And if it's cached, if you can do some intelligent things so the user never notices that it took 3 seconds for something to make it to all the machines, then even better. Good?
I had a question about splitting the tables into different servers. Would you be able to create, say, a database filled with views of tables on different servers, such that it would see?
Sort of. So that's a couple of higher level concepts. So basically, the question is, if you split data across many servers, could you potentially, if you split tables across many servers, could you potentially create like one machine with a bunch of views so that it has access to everything? You can kind of do that. So there's a storage engine called Federated, which allows you to access tables in remote databases. And then, of course, you have views themselves, which only let you access locally, but you can create them over federated tables and such. I wouldn't necessarily say it would buy you much. So we'll come to the further evolution of these systems, and I think splitting on the table level, just moving one table to another system, can be an easy way to sort of buy some time, basically, but it's never really going to be the final solution for most systems. Yeah.
Before you go into making this database more scalable, some applications, a lot of Web2 applications, they are like user-based, right? So that user has intents like 100 reads and 20, 30 writes and stuff. So you can just vertically split them by users.
Coming to that. OK. So you can use replication to help you out a bit, particularly if you have a very read-heavy application. Replication might be just enough to make your system work for the indefinite future. So for a system like Slashdot, for instance, they ran for a very, very long time. I don't know what they're currently doing, actually, right now. But they ran for a very long time, and maybe still to this day, using really just replication to scale reads. But typically, especially in Web 2.0 systems where you have this capability to really easily write things to the database, just by clicking one button and not having to reload pages and such, where users are tempted to just keep clicking, you end up usually in a situation that's very write-heavy, or that it's largely write-heavy. So you still end up with too many writes in some parts of the system, or you end up with particular tables like the user table or the contents table or something like that, that just gets the lion's share of the writes, and there's no good way to just split that off to another system. Additionally, when using replication, replication in MySQL is asynchronous, which means that the slaves are not guaranteed to be up to date at any given point in time. Usually they are, and in any given system, it's fairly likely that you're going to be able to keep up, unless you're sort of in the extreme edges of how many writes you're pushing through the system. But even if you do largely keep up, replication is not guaranteed to be synchronous. You're not guaranteed to have a write on the slave once you write it on the master. Which means that in the typical flow, let's say you have a web application where you write something to the database. So the user adds a post to the database. So they type in subject and content and all of that stuff. They click post. In the naive way to scale that system, you would typically take all selects and send them to slaves. So anything that's a read, send it to a slave. And that's a very easy way to accomplish that. But the downside of that, of course, is the user clicks post. The next thing you do normally is either refresh like a threaded view or refresh a page with the content that they just wrote. And oftentimes you're reading that out. You're reading that back out from the database. And if you're reading that out from the database from a slave, even though you've just written it on the master, it may not be there yet. So you have to do a lot of thinking in the flow of using the application to make sure that you don't end up in those situations where the user writes something and then they can't read it back, or they see stale data instead of what they've just written. And you find lots and lots of websites that have that problem today, where you go and you write something, you click on something, and the change isn't reflected in the page that loads immediately after that. And I think Meetup even has some of these problems. I've had some problems with that on Meetup. Yeah.
What about Google's synchronous replication patches?
So that's a good question. A little bit out of the scope of this, but Google has actually released some synchronous replication patches thus far only for 4.0, specifically for 4.0.26. Those are pretty interesting. They don't actually solve this problem, though. So they solve a completely different problem, which we'll come to in failover, which is ensuring that the slave has received the rights. They don't help you in the application design to make sure that the right, because they don't actually check that the rights are committed, just that they've been received. So yeah, essentially they've been acknowledged by the slave, flushed to disk, et cetera, but they haven't necessarily been executed on the slave. Okay, so the overall problems with replication and everything else means that you often end up doing a lot of work or annoying users. So you want to be fairly smart about what you do work on, and you obviously don't want to annoy users, especially this early in the game, developing the website. If you start annoying users and they don't like the site because it's it's falling behind and all of that, then they stop coming, and you don't have a problem to deal with anyway. So the stage immediately after that this is usually where you've built up enough of a user base that you have scaling problems, but you haven't built up enough knowledge to know how to deal with it. So I usually call this the sort of late teens to 20s stage, the awkward stage, basically. This is where you can easily die just by making bad decisions. If you decide to continue annoying users, for instance, you can die very quickly because your site becomes irrelevant or your product becomes irrelevant. People don't like it. Or you can die very quickly because maybe you didn't have good backup processes in place and you had several single points of failure and maybe you lost some disks. You just lose all of your data. That's an easy way to die a quick and fairly painful death. Additionally, when you try to actually move from the sort of teenager stage into the adult stage in a properly scalable system, this is often the first real project where it requires a fair amount of initial documentation and specifications and processes in place in order to do it right and not break everything. And of course, at this point, downtime is pretty difficult because the size of your user base means that you can't just take the site down for a weekend necessarily, because again, you come back to annoying users. And sites being down for multiple days because it takes a long time to copy your database around and import data and such is a bad thing. And obviously, the end goal, basically the next step after that is you have at least a fairly scalable system that can grow for a long time. An easy way, I wouldn't say an easy way, actually. Maybe easy is the wrong word there. But a typical way to accomplish this is through data partitioning. This concept of horizontal partitioning, basically, let's say we have a site based on users interacting with each other. A typical way to partition would be on users. So we have one group of users on one server, or one group of users on another server. How you accomplish that is sort of up to you, and there's a lot of ways to do it, which we'll start talking about after this section. But the basic idea then is that you've split things up by something. Often that is by user, but it could be by anything, depending on what you're building. With the theory that you can keep adding more of those things, and when you sort of reach your capacity with your current hardware, you can add more hardware and add more of those things to that new hardware, et cetera. And hopefully at this point you've built the system so that you can do incremental improvements without any major downtime. So you should think through, not only how do we make the system work, how do we make it fairly scalable, but how do we deal with it in the future? Let's say this architecture doesn't work, or we need to make some other things, something like that. Hopefully we can at least think about how to design the system so that incremental improvements can be made without any major downtime in the future. Any questions so far? Anything that has been asked? Pretty straightforward. I was thinking of adding a retirement, but you don't ever really retire in this sort of game. You end up still maintaining the systems perpetually as an adult, basically. And additionally, I couldn't find a good picture of like Cabo San Lucas, so I didn't have a good thing to put on the retirement slide. So next session, we'll just talk a little bit about partitioning, data partitioning particularly, sometimes called horizontal partitioning, user-based partitioning. People call it any number of different things, but it is basically the only game in town in order to build scalable databases. And whether it's accomplished completely internally by the database, or whether it's accomplished by code that you wrote, or by some open source libraries, or by whatever, it's effectively the only game in town. So if you look at something like Oracle RAC, it's effectively doing partitioning in the background for you. If you look at some of the MySQL solutions, they're typically application-based, and they're doing the partitioning on top of the database and just pretending that it's one big database, even though it consists of many actual underlying databases. A little bit about what partitioning is. It's effectively just distributing data on a record-by-record basis. And this isn't typically, as you think of a single record, like a single row in a single table, but rather in the larger scope of a record, of a user, for instance. You have a user record, but you also have lots of other things related to that user record, whether it's your actual content or groups that you belong to or whatever it is. You have a lot of things related to that. And we normally call the thing that you decide to partition on a partition key. So let's say you decide to partition by a user. Your partition key may be a user ID. So a big int or an int or something like that. That's your partition key. A given application may actually have multiple partition keys if it makes sense for that particular application. So there are many where it does, where you may partition both by user, and then you have some larger concept like groups, for instance, where groups have their own content, and users belong to any number of groups and such. And it may make sense to partition both by user and by group, even across the same hardware. So the same hardware, the same physical box may have 1,000, 100,000, whatever users on it, and 100,000 groups on it, but there's no real intersection between those. It's not groups for a particular user or anything like that. It's just they happen to share the same hardware. So an application may have multiple partition keys. Each partition node has all related tables, but only a portion of the data. So in a typical system, you may have 50 tables related to the content that a user produces. And you still need all of those 50 tables on every partition. But each of those sets of 50 tables only has a portion of the data. So all of the data for a particular user will be on a particular machine. There are a lot of different ways to go about partitioning, and we certainly won't talk about all of them, but just a couple of interesting ones. Excuse me. The typical way to implement partitioning, if you just start hacking away, writing some code today, and what you'll see a lot of systems have implemented, and you can see a lot of presentations by various companies and such, the easiest way to do partitioning is what I usually call fixed hash key partitioning. So you effectively define a key, a hash basically, to start with, and you have to sort of stick with that hash long term. And I'll go into some more details about how that works. One step up from that, and what's often a lot more scalable, is what I normally call dynamic directory partitioning. So this is a dynamic partitioning scheme. It isn't fixed in that you have, if you think of the simplest hash key, we could say a hash. A hash is just something that takes an input and returns an output. And by it being a hash, it's normally returning an output that it's a one-way hash, so it's not easily reversible back into the original input. But this could be something as simple as saying, users with user ID 1 through 100 go over here, 101 through 200 over here, et cetera, et cetera, et cetera. That's a very simple form of a hash. It could be very complicated. It could be something based on an MD5 or a SHA-1 hash or something like that. It doesn't really matter. It could be random, actually, in many cases. But the next possibility, the dynamic directory partitioning, just implies that you keep track of where you put things so that you can find them later. So rather than having a fixed way to designate where something goes, we just put it anywhere, but we keep track of where we put it. And we can then, in many cases, move it later, which is the biggest benefit of dynamic partitioning and why it's called dynamic instead of fixed. You can't move things in a fixed hash key partitioning system. You can in a dynamic directory partitioning system. There's a couple of major concepts. And you have to, when you build a partition system, you have to choose a partition key. That isn't necessarily easy in many cases. Partitioning by user or user ID isn't always the best idea. If you think about many applications, you may have a lot of very intensive user interactions. So anything like, let's say I upload a picture of myself, for instance, or I upload some content about myself. That's very easy to deal with because we know it goes in the Jeremy partition. But if I send Eric a message, where does it go? Eric and I may be on two different pieces of hardware, two different database servers. Where does that message get stored? Any ideas? One user sends another user a message, and you're partitioning by user. What are your options? So you have a couple of options. You actually have effectively 3 options, and not all of them are very good. But you could store it on the sender side. Obviously, that's not good because your primary purpose is that someone needs to receive it. So in order to find out that a message has been sent to you, you need to be able to find it fairly quickly, and that doesn't really work well. So you can store it on the receiver side. And that works actually really, really well and is very scalable because you send a message to the user and it's stored over there and you don't have to worry about it anymore. The problem then comes that the manager says, well, I'd like to have that like a sent items folder. And well, oops, we've stored all of those messages only on the receiver side, so there's no good way to get the sent items folder for the senders because they're on any number of different machines. So the typical case is actually that you store, if not the entire data itself, at least a reference to the data on both sides, both the sender and the receiver. Effectively, you duplicate data. In many cases, you actually just store the whole data because data is fairly cheap, particularly that sort of data. And the extra lookup for each message, for instance, if you needed to get the content of 10 messages, you may have to contact 10 different partitions, which could be 10 different actual servers. And that gets ugly very quickly. So it's very common to just duplicate the message stored on both sides. So some of the basic difficulties with partitioning systems is that the number one thing is that interpartition interactions or dependencies become a lot more difficult. So it's not just things like sending a message from one user to another. It's anything where you think about multiple users. If any sort of interaction could touch multiple users, you have to think about how to implement it. So a couple examples of that. Sending messages is one of them, and that's the example that I throw in there. But the second example is something like a friends list. If I have a list of friends and I want to see the name and the location and the email address of all of my friends, how do I get that information, right? I probably, at least on my partition, I have a list of the friends, but that list is probably just IDs. So how do I get the rest of the information I need? The short answer is that for most of those interactions, you probably have to talk to multiple partitions. And you have to design your processes and internal applications and such so that those interactions don't implicitly have to touch everything. So if you, for instance, limit the page to display 10 friends at a time, then you have an upper bounds on the number of partitions you could access. If you set the users up with the concept that they have an all friends list that they can always access, and now a user has 20,000 friends, there's pretty much nothing you can do to scale that particular page loading. So part of that is actually sort of setting expectations, I guess, on the users. Part of it is just actual scalability. Overall reporting becomes a lot more difficult because especially the managerial types like to know things about where their money is being spent and whether things are growing, how they're growing, where we should spend money advertising, all of that sort of stuff. So they want to know a lot of stuff that you can't really plan for. And that all of that stuff becomes a lot more difficult. So you want to find out the average number of messages sent per user by state. So we want to know that users in Tennessee send an average of 4.5 messages a day, and users in Idaho send an average of 2 messages a day, and users in California send 10 messages a day. And that sort of stuff is very, very common to need to find out because people need to know that stuff in order to figure out where to spend their advertising dollars, or figure out how to improve the site, or whatever the case may be. And obviously that's a simplistic example, but so the average number of friends a user has by state, another interesting one that's hard to do. We're not talking about solutions yet, just problems. So the second problem that you have mainly is you have to decide what to partition by, and that's not always an easy decision. But I would say that in most cases, partitioning by something like the user or whatever its equivalent is in your given application usually allows for the most flexibility in the most applications. There are exceptions to every rule, of course, and that's by far not hard and fast rule that you should always partition by user. In some cases, it makes sense to partition by, for instance, groups. So if a user never interacts with things that aren't in its group, and you could partition by group, so that basically every group of users is on the same piece of hardware. That makes some interactions easier. So things like sending a message from one user to another, very simple. You don't have to duplicate it. You don't have to do anything special. If you ever allow intergroup interactions, or if you ever allow users to interact with users in other groups, That sort of stuff is often, it happens as soon as you implement some of these sort of arbitrary rules to say users can only interact with their own group. Someone comes by and says, in order to get that $20 million of VC money that we want, we need to allow users to send messages to all users. OK, now we've broken our entire partitioning scheme, and we have to rewrite everything, right? So one of the interesting cases you have is that you can get at least most of the same benefits without some of the same headaches, and at least with more options for the future. If you, for instance, partition by user with an affinity based on group or based on whatever, so that you hope that all the users that are interacting mostly with each other are on the same machine, but there's no exact guarantee in the database. So you can get some of the performance benefits. You can get some of the sort of fringe benefits of that without limiting yourself to say that we could never send a message from one user to another user that's in a different group. One of the other interesting problems that partitioning by group has is that you often end up with groups that are much, much larger than other groups. Whatever the group designation is, it could be a university, it could be a company, it could be whatever. So you'll have thousands and thousands of 2 and 3 and 4 person companies on a given system, and you'll have a few companies like IBM where you could potentially have tens or hundreds of thousands of employees that are in a single group, and it may be very difficult to scale those larger groups in the overall system. And the same goes for things like universities. A few of them are much, much larger than all the rest.
Why is it necessarily faster to have the related data on the same database?
It isn't necessarily. It depends on what sort of interactions you're trying to do. It basically means that you could potentially have fewer round trips to the database, and you could potentially, let's say you want to get I don't know, the names of the first and last name of all members within a particular group. You could potentially issue that to a single machine as a single query, rather than having to issue it to all of the machines in a particular partition system.
And if you don't necessarily know that those users are located on that machine, you just hope those IDs are there, and then if they're not, have to go to some directory to find them?
It depends on, it depends on too many factors, I think, to necessarily say. But there are certain types of interactions that could be a lot faster if they were done only once, rather than once per partition. And there's not necessarily that's not necessarily a good reason to say that you would want to do affinity or that you would want to do partitioning by group, but it is definitely true in many cases. So. OK, so if we look at the partitioning possibilities, starting with fixed hash key partitioning, and we're actually taking a long time here. Fixed hash key partitioning is basically, it's fixed as the name implies. You divide the data into any number of buckets. We'll call that B. We divide those B buckets over M machines. And we could take an example like we define 1,024 user buckets. And that's a pretty common number because it's a fairly nice number. It's a power of 2, so it's easy to divide many different ways. And many hash functions and such will easily get you to 1,024. So we have buckets 0 to 1,023, but we've only got 4 physical servers, so we need to divide those 1,024 buckets over those 4 servers in some logical way. We could do a modulus again on that, for instance. We could do 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, sorry, 0, 1, 2, 3, 0, 1, 2, 3, et cetera. We could do ranges. We could do any number of different things to get them onto the 4 physical machines. But there's a few problems with that. First of all, the biggest problem, one of the first problems that you would notice is that you limit yourself to the number of potential machines you could ever scale to. So it's tempting in many cases to choose a smaller number that's easy to work with, so 256 or 128 or something like that. But you're then thinking, well, I could see us having 128 servers in 3 years. So 128 partitions maybe isn't enough. So let's bump the number up. So let's say 1,024. In any case, you're limited to a particular number that you have to choose at the very beginning. Essentially scaling the system means at very minimum, you generally affect 1 over the number of buckets that you've determined of your users. So if you have 1,024 buckets, you affect at least 1 over 1,024 of your users in the best case. In most simple implementations, you actually generally affect 1 or 2 over m of your users. So if you've got 10 machines, you may affect 1/10 or 2/10 of the users, because it may not necessarily be easy to just pick a whole bucket up and move it from one server to another. You may have to do some things on the server level in order to be able to move the whole bucket efficiently. In any case, there's no good way to move it atomically. The bucket to machine mapping has to be stored somewhere. It's often stored in code. So the ranges or the modulus formula, whatever it is that you've used to determine how to distribute those 1,024 buckets over the number of physical servers, that has to be stored somewhere. And in order to be able to move those buckets, not only do you have to move the data in some sort of atomic fashion, you have to update that bucket to machine mapping atomically across all of the clients that need it. And that's actually really, really hard to do. Additionally, you have no real control over exactly which bucket and thus which machine a given user is assigned to. Typically, you could see something like an MD5 or just a modulus or something like that to get you to 1,024. And you could do a range or a modulus or another hash function to go from 1,024 to your 4 machines. But there's no way to say, this user is much busier than the other users, so we need him on another machine. You would either have to special case that particular user or sets of users, or you just sort of give it up. So if you have particular users or particular groups or whatever you've partitioned by that are much more expensive than others, there's no good way to deal with them. Questions so far? How many of you have seen a fixed hash key partitioning system? Good. Good. All right. So the next basic option, and the sort of natural evolution, actually, of the bucket to machine mapping in many cases, is some sort of dynamic directory to assign them. Using this dynamic directory concept only for the bucket to machine mapping in a fixed hash key partitioning gets you most of the hassle of the dynamic directory itself and all of the code that you have to write to support it, without most of the benefits, which are the ability to deal with individual users. So in this dynamic directory concept, you have a directory server, and I call it a server, but it could be anything. It could actually technically be a text file if you really wanted it to. It's just a place where you have a database of mappings between users and partitions. So you essentially map a user ID to a partition ID. So you have 10 partitions. You have 1 million users. Somewhere there's a mapping with 1 million entries that maps user ID 1, partition ID 1, user ID 2, partition ID 2. Whenever a new user comes in or a new thing is created that you've partitioned by, you would assign that often randomly, but it could be based on round robin or based on a hash or something like that. You assign it to one partition, and that mapping is stored in the directory. A user can be moved later using some magic around the directory concept and hopefully some implementation details that you've implemented in that directory concept, so that you can move a user by locking the user, moving their data, updating their mapping, and unlocking them. The key point being that you can deal on a user-by-user basis. So you can, for instance, move one user from one partition to another effectively atomically. Since the amount of data that you have to move one user is typically fairly small compared to 1/1024th of your data or 1/nth of your data, that means that you can make those individual moves much quicker. So that individual user would have to log in during that 3-second time frame while you're moving them in order to experience any downtime, basically. So only single users are affected by any repartitioning. Partitions can be rebalanced, and that's another key point, is that even though you've balanced, for instance, users across partitions in a fixed key system, you haven't necessarily balanced load. Because the users themselves, some users may generate vastly more traffic than others. So if you host let's say you host a blogging site, most of your users are probably small time, 1 entry every 2 months sort of blogs. And then you get someone from CNN that wants to syndicate their blog on your site and do all this fancy stuff with you as a partner, but they're much busier and they get a lot more traffic. So now you've got this problem that this one user is, you can't move them, you can't do anything special with them. because they're assigned in a fixed way to one partition within your system, and they have to live with the rest of the system. So to get them more capacity, basically, you have to buy more overall capacity. Question so far? Yeah.
Does it make sense to make that directory like an actual directory, like LDAP?
I haven't seen anyone do it with LDAP. MySQL is usually the typical choice, just a specific MySQL database that acts as the directory server, basically. I would say it should be a database of some sort that supports indexing and all of that fancy stuff. But it doesn't necessarily have to be MySQL. It doesn't have to be anything in particular. Yeah.
You know, it kind of it's too thinking about MySpace type, scalable systems. But I think the next evolution might be federated, where they say, okay, there's a, in sites, especially smaller sites, they federate, like the users are open users, right? Open ID or claim ID, those kind of scenarios, where the site doesn't necessarily own the user in that sense.
Okay.
And that's like, so there are different databases, not even MySQL.
But the only interaction that you would typically have on a site, so in the case of OpenID, for instance, the interaction you would deal with where you can take advantage of that being if essentially federated users is really the login. OpenID doesn't have any mechanism to store the user's data back on wherever they're coming from. So you still end up in the same situation, although maybe you've eliminated some of the hassle of the login part of things. You still have to store the user's data, which is the bulk of what you have problems scaling typically. Is this thing like flashing colors? OK. I keep seeing this out of the corner of my eye, like red and blue flashes. Yeah.
So is the directory server a single point of failure potentially in this setup?
It is a single point of failure, yes. But in the sort of overall model, there's nothing so far implying that any of the particular databases are not single points of failure for that piece of the pie. The directory server is definitely the most important database in the system. But in the high availability side of things, it doesn't necessarily have to be exactly a single point of failure. So you would typically, each partition would be highly available, and the directory server is basically just a special partition. So it would also have the same high availability. And there's a lot of failover solutions for that. And there's MySQL cluster, for instance, which you could use for the directory server without using it for the data. That would be a fairly decent idea, depending on the application.
So what's wrong with storing in a cookie? The directory, it's like a distributed directory server. I mean, if it fails, if the cookie is deleted or something, then you
can store a cache in the cookie. But you couldn't store the authoritative source of the data in the cookie. So you can certainly, yeah, I mean, we won't talk anything at all about caching on the client side things, but you could certainly do a lot of interesting stuff to cache some of that on the client side so that you don't have to look it up constantly on the back end. So, any questions? All right. Just we'll try to go quickly through some of this other material. Some of it's very specific, and again, the presentation is available, and I'm available for questions. So, lots of people have built their own partitioning system. So there's a ton of custom solutions out there, and you can build your own if you want. It's very, very easy to implement fixed hash key partitioning. That easily gets your data distributed. When I talk about these things, I usually say basically that's the easy part. Getting the data onto multiple systems and off of those systems is really, really easy. Getting that system to really scale with minimal downtime, getting the ability to rebalance things, all of that stuff is much, much more difficult. So just the simple fixed hash key partitioning, it's great. It works really well to get the data distributed. It doesn't necessarily work well in the really long term because of its inability to rebalance things or move data fairly easily. So it's much more difficult to repartition. Repartitioning, in many cases, the simplest way to repartition is to just split one node into two, for instance, which often means you end up scaling in the powers of 2. So you split from 1 to 2, 2 to 4, et cetera. And that's the easiest way to scale because it means only one partition is affected at a time, but it's also the most expensive way to scale. It's approximately the same cost at the very beginning. You know, if you plot things out on the nice line graph, exponential versus linear looks pretty close together right at the beginning, and then there's some point where it just sort of diverges, where it gets much more expensive once you cross a certain threshold, and it just keeps getting more and more expensive to scale those systems. So it's difficult to grow because adding more machines means repartitioning in every case. There's no good way to not repartition. Hibernate Shards is one solution that was announced. I guess Google actually created it and contributed it back to Hibernate. What was it, 2 months ago maybe? It's kind of emerged between fixed key partitioning and directory-based partitioning, and I won't talk a lot about it. It has this concept of virtual shards to abstract the mapping, pretty much how the bucket to machine mapping works in the fixed hash key partitioning. It's still painful to repartition, and the Hibernate Shards project itself doesn't do any of that for you. So it's assumed that you can handle it yourself. It doesn't handle rebalancing at all, and it doesn't handle aggregation at all. So any sort of access of multiple partitions, you're on your own. There's a new, fairly new project, actually older than Hibernate Shards now, called HiveDB, which is one that I won't claim to have written, but I actually sort of came up with the idea for it through many, many customer visits where, doing MySQL consulting, many of our customers ask, how do we do this wonderful partitioning stuff that you're talking about? And it used to be the answer was basically there is nothing out there, so you have to write your own. At some point, maybe 6 months ago, I started telling customers, instead of telling them there is nothing out there, I started telling them that there is nothing out there, but you should write one and open source it. And a few customers finally agreed, mainly Cafe Press has done the largest part of the work on this. So they've created this project called HiveDB with my guidance and oversight and everything like that. And it's basically an open source implementation in Java of really the entire standard partition by key directory-based dynamic partitioning scheme. It's implemented originally sort of a rough cut by Fortress Consulting, another consulting company, and then Cafe Press picked it up and made it their baby and has been working on it for many, many months now. Many companies have built similar systems to it, but no one has open sourced it. And it's pretty cool overall. You should check it out. So HiveDB actually works in Google now. You can search for HiveDB, but it's hivedb.org. And really the reason HiveDB exists, and I'll sort of push you on it, you could use Hibernate Shards right now. It's, in my opinion, less mature than HiveDB. And they're both Java solutions anyway, so you're stuck with Java either way. But many solutions exist that only solve the easy part, and Hibernate Shards is no exception to that, which is just storing and retrieving data across many machines. Nobody has really touched on the hard part, which is being able to rebalance. That's one of the main hard parts. Not only having the ability conceptually to rebalance, but having the code in place to actually do it. And HiveDB currently today can do that. So you can actually have it move one user from one partition to another. Additionally, it has some management infrastructure on top of that to allow you to create essentially callback functions to determine how expensive a user is and be able to move things to have the Hive system balance itself dynamically. One of the other hard parts is aggregation. Aggregation is currently not touched on by HiveDB, and I mentioned that briefly in the Hibernate Shards. It's basically you have a query that there is no good way to answer. So you want to find out the average number of messages sent by all users in Tennessee. If you've partitioned by user ID, users in Tennessee are scattered across all of your machines, so there's no good way to connect to one machine and issue a query that will get you the answer you want. So the only real solution is to connect to all machines, issue some sort of workable query, and then aggregate the results of all of those queries into a single result that you actually want. And that's part of the HiveDB spec. It hasn't really been written yet, but will likely end up being another sort of middle tier that sits above the above the Hive itself and allows you to issue aggregation to the entire Hive. But the Hive HiveDB server architecture, you basically have a Hive metadata database, which is Hive metadata itself, which is the partition definitions. Those are in XML files. Sorry. Those are actually in both XML files and in the database. So there's pieces of it. The schema definition, which I didn't list as a bullet point here, is actually in XML. The partition definition itself is another piece of metadata, but it's in the database itself. So which partitions exist and various flags for them, like whether they're read-only and that sort of stuff. Whether they're considered full, so we shouldn't write anything more to them, just use them for the active users that are already on them. So the directory itself contains partition key to partition mappings and secondary key to partition key mappings. So user ID to partition ID, for instance, is the partition key to partition mapping. But then you may, let's say you have a user that needs to log in by email address. That's pretty typical for websites. You don't usually have a user type in some 9-digit ID number to log in. You have them type in something familiar like a username or an email address to log in. So those are considered secondary keys. They're things that you don't know which partition they belong to without having a mapping somewhere else. But you need them from the front end, basically. So you need an email address, but you don't yet know what user ID that is. So you can't just map email address to partition ID. You need email address to partition key. So email address to user ID to partition ID. And that gets you to the right machine. So Hive has those concepts within it, partition keys and secondary keys. There's a concept of a Hive queen. That is the management and rebalancing decision maker. So a daemon, effectively, that runs and makes decisions on how to balance the system. A job server that actually executes those tasks. So the Hive queen actually creates tasks to be executed. The job server executes those so you can control the rate at which they're executed and how many machines are executing those jobs in parallel and all of that fun stuff that you can do with job servers. And then a future component, which is currently roughly spec'd out but not developed, is the aggregation layer, which is just another part of the API, which would sit on top of the HiveDB structure itself and allow you to issue queries to all partitions. The idea behind that rough cut is basically it would be an API in Java. You issue a query using SQL to no particular partition or to a subset of the partition list. So you could potentially provide a list of 5 partitions to issue the query to. It will actually, in the background, issue it in parallel to n number of partitions at a time, receive all of the results, aggregate them, and then return a single result set handle to you so that you can then walk through it like a normal database result set. In most cases, that would likely be implemented as a web service. So you would never rewrite that code. You would never touch any of that code from like PHP. You would issue a web services request and get that stuff. So the big question in many of this is, I don't use Java, so what do I do? And HiveDB, actually, we've basically designed it so that you don't have to use Java. All of the hard stuff is in Java, and it's going to stay that way, and you never would want to rewrite any of that yourself. The easy stuff is the Hive API, basically figuring out by talking to the directory server where data exists and then giving you a connection handle to the right database machine. That you're basically expected to implement in any language that you need it in. So currently, there is an implementation in Java, but we would expect that someone will write it in PHP, and someone else will write it in Ruby, and someone else will write it in Python, and it will know how to talk to the Hive metadata database to find out the partition list, and then be able to do lookups on user IDs and that sort of stuff. And no one has written any of those yet, so if you want to write one and you want to build one of these applications, let me know, and I'll put you in touch with the right people to make it as easy as possible. So the client architecture, the client side of things, is that the client uses the Hive API to request a connection. Once it's received the connection to the right database server, it can use that just directly to talk to that database server. So you would typically, user logs in using their email address. Through the Hive API, you can pass that email address as a secondary key lookup. It will return a connection to the correct partition for you. And you can then use that partition connection to do any work you need to do for that user. The Hive API components of it, it's expected that, like I said, those would be written in each development language as necessary, because it would be fairly inefficient to request a connection from Java to be used in PHP and all of that. Questions? Yeah.
The Hive API is the fixed partition only, right?
Sorry?
It's a fixed key hash key.
No. It's dynamic.
Oh, it's dynamic.
Yeah. Yeah. So in the Hive DB model, like I said, the hard parts are the Hive Queen, which is the management layer, and the Hive metadata stuff, which is the whole directory server layer. The easy parts are really the client API. The client really just connects to the Hive metadata database, issues a few queries there, up to a few queries, generally only one, and then connects to the correct partition and gives you the connection handle for that partition.
So presumably that client will respect any sort of locking that's being done if the queen does it.
Yes. Yeah. And the reference implementation does that, so you can just copy what it does.
You said that aside from the aggregation layer, this is mature enough to use today?
Yeah, absolutely. In fact, it's in production in a few places already. Yeah.
Does it do connection pooling and things like that?
It doesn't inherently do it, but yes. So it isn't exactly part of the Hive model in that sense that connection pooling is just another component that sits in the overall stack, but it isn't implemented as like Hive doesn't have its own connection pool. It uses whatever connection pool you want.
So can we use it? Is it interoperable with something like Hibernate?
In what sense of interoperable?
So can I actually front end this with Hibernate to essentially map or essentially hide myself from the implementation?
So I am not a Java guy. I could probably not answer that question for you, but there's a HiveDB mailing list where they could answer that. So like I said, I did oversight of the MySQL side of things and make sure it's written correctly. But as far as like exactly what you can and can't do with it in Java specifically, couldn't answer those. Yeah.
Say one wanted to cache the result of the database partition key or primary ID mapping.
It's actually
the Queen Hive would be able to invalidate.
It's actually already inherent in the system. Okay. So you can just choose to use memcache, and right now it only supports memcache. But yeah, it's an optional but usually present component. Yes. Yeah.
This is kind of cool because I mean you could scale the Hive queens actually, or the directory server, because if let's say you don't find any local directory, like going back to the ID thing, right? And if there's a web service for the directory servers to talk to each other, I mean they could discover where that particular user is. So it could be fundamental to the internet in terms of, I mean, this not necessarily hyper-specific information, the concept of discovering the user and saying, oh, okay. You just delay. It won't come in 2 seconds maybe, but
Sure. Yeah. I mean, you could use it for a lot of interesting things. Actually, one of the things I've been thinking about is using the HiveDB model to store blobs in a scalable way. So storing things like images and such, because the backend system is very, very scalable. The only real sort of hard limitation is that in reality, there has to be a single list of all partition keys and their mapping to the partition that they live on. The number of those that you could potentially have on modern hardware is very, very high. So there aren't any real concerns that you're going to sort of exceed the capacity of that machine. And again, since it's just the directory server, you could potentially scale that problem by throwing hardware at the problem up to a pretty high extent. So if you're talking 10 million users, 100 million users, 1 billion users, those are easy to scale with that level of scalability. It's difficult. If you wanted to have 1 trillion keys, for instance, that would be pretty hard to handle, because the database for the directory server in most systems, in order for the system to be fairly responsive, it should fit on a reasonable sized disk subsystem. It should fit partly in memory. But if you're talking 100 million users that would use your website, or that you have that many partition keys, absolutely no problem. Yeah.
And the example you cited for the secondary keys, you said you map email address to user ID to partition ID.
Sure.
But maybe this is naive, but wouldn't we just use the email ID as the user ID and skip that step?
You could. But so the key is basically, you would normally, you wouldn't want to do that in order to avoid lookups on the directory server, basically, because it's very likely that whatever partition key you end up at, that's the key that you use across everything. So it's very common to use like a big int or an int as the user ID, because you have to duplicate that in any number of different tables to make reference to that user. So in reality, that is your key, and you need other keys to look up into that, like an email address or a user name or something. But you wouldn't want to store an email address millions of times in a database. OK, we may have to skip most of the high availability stuff. It's already 8:30. We just keep going until 10, typical time frame. Let me just talk quickly on high availability, just a bit of a skim through here. And the slides are online, so. Yeah, I've given the talk on replication before, and eventually I should repeat that one. But the usual replication setup and the usual setup that we'll look at for high availability is based on dual master replication, which is two machines that are master and slave of each other, but only writing to one of them. Don't use ring replication with more than two. So we'll jump to high availability options. Dual master, two machines, independent storage, master and slave of each other. You could potentially have any number of slaves additionally for reads if you have a problem scaling reads. One consideration that we would say, actually, and that I tell many customers is, rather than trying to sort of shoehorn slaves into things to get additional read capacity, in many cases it's easier and more administratable to just add more partitions. So if you need more capacity overall, unless the number of reads to writes that you have is out of whack for most websites these days, which means that you've got, that you have a problem scaling reads, first of all, which implies that you have some sort of user-based system or write-heavy system. If you additionally have a problem scaling reads at the same time, that would be fairly atypical, I would say. That often if you have a problem scaling writes, that implies you need enough partitions to handle that, which automatically gives you enough capacity to handle the reads that you need to do in many cases. But nonetheless, if you still have a problem scaling reads, you could partition further than necessary to handle the writes, or you could add slaves. Neither solution is necessarily cheaper than the other, but at very least, partitioning further on the writes gives you more options for future scalability, future features, where you may become more write-heavy. Shoehorning things in, changing a lot of code to add slaves and make those work properly may mean that 6 months down the road, you add a bunch of new features that add a lot more writes to the system, and the slaves don't help you anymore. So you've spent a lot of time and wasted a lot of effort to make that work without any real gain. So the dual master scenario means two machines, independent storage, master and slave of each other. Configuration is really simple, all of that, and you can read all of this online. Dual master by itself doesn't help you scale writes at all. Don't write to both machines. Even if you do write to both machines, it still doesn't help you scale writes because both machines still have to execute everything. So just don't do it. It's limited to 2 sites, et cetera, et cetera. To scale writes, you can put dual master underneath of horizontal partitioning. So we'll put this all together at the end. So the dual master scenario gives you high availability. It doesn't help you scale writes. The partitioning scheme gives you scalability. It helps you scale writes, but it doesn't give you high availability. So the partitioning schemes, like I said, they don't address HA. And typically, HiveDB is a case of this, and Hibernate Shards is another case of it. They just treat the shards or partitions as a single MySQL server. You're responsible for making that single MySQL server highly available, either through DRBD or a SAN or dual master with failover or whatever you can think of to implement HA. So you implement an HA solution for each partition underneath of the partitioning scheme. And a good way that I would recommend to do that is HiveDB for partitioning, dual master with failover solution for the HA part of it. While it's not technically perfect and you have a very small chance of data loss, with decent monitoring and such, you can limit what that might be. It is generally the easiest to administrate and the easiest to deal with long term. There are SAN solutions and DRBD solutions which may give you some sort of more technically perfect, no chance of data loss kind of scenarios like DRBD, synchronous replication on the block level. There's no chance that you're going to lose data, but there is a very high chance, and in fact, a guarantee that when you fail over, it's going to take a long time for it to come back up. Dual master, that's not the case. So you may lose a little bit of data, but you won't be down for 40 minutes while it recovers. And with some decent monitoring, with some decent things on top of that, you can make sure that the amount of data that you've lost and that whatever you've lost is sort of known and potentially recoverable. Because you could potentially recover it from binary logs or from the other machine whenever it comes back. You can manually fix things. But we're talking on the order in most systems of milliseconds. So it's not like you're losing 10 minutes of data or anything like that in a typical case. You're losing 2 milliseconds of data because that's what was missing when you failed over. LVM is a very good idea, and I won't talk anything about that. But LVM is the logical volume manager. Allows you to take snapshots of volumes. Use it. Love it. Any questions? Comments? Discussion? Yeah.
Get the replication. So is there a single way to check those slave and master, the differences that tables have?
Kind of. So not exactly. It's not in the sense of, if you have two machines that you can just compare them. The only way you can really tell the difference is by looking at binary logs, which is, in the replication scheme, MySQL keeps logs of everything that's changed effectively. So by looking at the positions in those logs, you can then sort of derive what you've missed. But there's nothing to automatically merge the changes. There's nothing to do anything like that. It's just a manual process that you would have to do to fix it. So the typical case would be basically, let's say your slave was running half a second behind and the master lost a power supply. There's a lot of weird edge cases which I won't really talk about, but let's just assume the slave was half a second behind, so you've lost half a second of data. When you fail over, you make the decision, okay, the master is not coming back anytime soon, and uptime is more important necessarily than the half a second of data that we lost. So we fail over to the slave. We start writing things there, so we assume that that's in a clean state at that point, right? We start writing new things there, so we can't, when the other machine becomes alive again, we can't just sort of connect them back and pretend nothing happened. So when we fail over, we should look at the positions in the logs that it was at when the master failed. And then when the master comes back, we can look at the logs past that position and see what we missed. Does that make sense? If we haven't missed anything, which is a typical case because you're talking about milliseconds usually, and either you've missed a very small handful of things or you've missed nothing, then you can just connect them back up and keep going. If you're on a particularly busy system, you may have missed a few transactions, and the proper way to fix that in most cases is to re-image that machine from the image of the machine that you're now calling the master, or the primary master, and then potentially manually merge any of the changes that you missed.
So you say the only way to check the difference is to see the log. Can't compare those two databases tables by record level?
So you can do it. You can't do it easily, particularly not without downtime. So the problem is not generally in comparing two things. It's comparing them while they're not changing. So in order to get to the point that they're not changing, you have to have some consistent state between them. And if you've started writing to this one, and this one's been down for 3 hours while you change the power supply, they're no longer anywhere near in sync. So now you're going to get not only what you missed because of the failover, but what has changed since the failover as a difference. So there's no easy way to, even if you get that, there's no easy way to do anything useful with it. Yeah?
So if you want to save some money, can the slave be not equal to the master?
No, don't do that. So that's a bigger topic, but yeah, in general, slaves will have to be at least roughly equivalent to the hardware of the master. In most cases, and particularly if you're looking at failover, so if you're looking at doing this with dual master failover, I would say in all cases they should be absolutely identical. Both for an administrative ease in the sense that you don't want to have to deal with the two machines being completely different and having to fail to one or the other because you can't support the capacity you need to. But additionally, because the replication process, typically you're bound by the amount of writes, essentially, that you can push through the system. And replication actually has to deal with the same writes that the master does. So just by that nature, it needs to be similar hardware. But additionally, it's doing them in a less efficient way in serial based on logs. And it's not going to execute them as efficiently as the master does.
Oh, in general? Or basically,
yeah, just in general.
I mean, it depends on the application, right? So if you're a stock application, I can understand that. But if you say you have 10,000 partitions, machines, and, mega...
But there's
then think of power implications. You have like 10,000 guys that are not doing any slaves, they're not really doing any constructive value. I mean, they might be failing once every 15 minutes, one machine or the other, but I mean, it's a trade-off. So
well, there's always trade-offs in that sense, but there's only one reason that you would have 1,000 partitions, which is that you need that for capacity. And if you need that for capacity, you're not getting that by not having equivalent hardware for the slaves. Because if you fail over and you have hardware that is not as good as the hardware you started with, so your B machine is less powerful than the A machine, then that partition has less capacity for that time. So your overall capacity is actually the capacity of the B machines and not of the A machines.
It's a problem anyway.
But if you're talking about 1,000 partitions, there might be better ways to do that anyway, rather than n times 2. If you really needed 1,000 partitions, there could be some other SAN-based solutions and such that would probably work better. If you're talking dozens of partitions, typically, n times 2, you're not looking at substantial differences. Additionally, having the dual master scenario gives you a lot of other interesting options with doing things like alter tables or adding indexes and such that take a long time and would potentially lock things without any downtime. You can do this. You can, for instance, add an index without any user noticeable downtime at all. You can't necessarily do that if you have weaker machines or if you have n plus 1 or n plus 5 or whatever as a failover scenario instead of n times 2. So. Questions? Yeah?
On a related note, like if people do want to add columns or indexes on large tables, is that typically what you recommend? Or do some people create like children tables that are actually separate, like as opposed to adding a column to a table, adding another table that...
So, yeah, in general, I would say that the best way to deal with that is dual master and using the dual master replication sort of failover model to allow you to do alter tables and any other maintenance tasks that you need to do without downtime. You can do things like adding tables instead, because adding a table is essentially free, but that only gets you so far. That helps you to add extra columns, but it doesn't help you to add indexes on existing columns or to change data types or anything like that. So it only solves one very small part of the problem, whereas the dual master picture would solve it all fairly easily. And it isn't that hard to set up. So it's actually sort of a quarter of a day project generally in most database systems to get dual master running.
Operations, does it handle deletes as well?
In what sense? Like, oh, if you wanted to do like a bulk delete of lots of data?
Or can you delete a column?
Yeah. Yeah. So the caveats, and this is sort of out of the scope, but in the dual master model, so what we're basically talking about, in dual master, you're replicating from one machine to the other and from the other machine back, basically. You're only writing to one at a time, and you ensure that you only write to one at a time, normally using IP takeover. So you have an extra IP address that every client connects to, and you move that IP address from one machine to another to move clients. So given all that setup, basically, you can technically at any time write to either machine. There's nothing to stop you from writing to either machine. So you can use that administratively to connect to the B machine. So let's say all the writes are going to A. You connect to B. You can disable binary logging to keep statements from being replicated from B back to A. So you can you run set session SQL underscore log underscore bin equals 0, which means don't log the rest of my session. You can then run any commands you want to do locally on that copy of the data. That will lock the tables, and et cetera. It'll cause replication to get behind while they run. But the logs are building up. And once your 6-hour alter table is finished, you can then either restart replication or just let it restart automatically if you never stopped it. And it will go ahead and get caught up with the current replication stream and basically just work. Once that's done, so you've added a new index that took 6 hours. Once that's done and you're comfortable that it's working correctly and you haven't broken anything, you move all of the users over to B and do the exact same thing on A. So stop replication, add the index, wait for it to finish, start replication, wait for it to get caught up, and then now you've got your new index on both sides. So you can then fail back or just leave everything on B if you wanted. The caveat to that is that it only works for non-destructive operations. So as far as dropping columns, you absolutely can drop columns, but make sure you stop using the column first. So if you drop the column on the slave side, but you still have inserts that reference the column name coming in on the master, those inserts will break when they get replicated to the new table schema. So you need to make sure that that column or that whatever is not being referenced anymore before you make any changes. So fix all the queries to not reference it and make sure it has a default of null and that sort of stuff so that it still works. Yeah. Yeah.
When users are infrequent, like they come once a day or something, and the sessions get really big, I mean, that user context data, is there something once again scaling that?
User context data. So
you get like literally megabytes of data stored per user.
What sort of application are you thinking of?
Well, Web 2.0, sort of like application. You go on, you're there for an hour or so watching videos and stuff, and all kind of stuff, and especially using the directory model, dynamic directory, so you're assigning to a particular server. So yep. I'm thinking in terms of where there's load balancing at the web server side too, not just the database side. So you kind of have a lot of session data. I mean, it's not relevant to database per se, but the session data is in the client. I mean, this is.
I mean, I would say it's atypical to have megabytes of session data. If you're talking megabytes of data, that's likely either historical stuff that you should be storing in some sort of historical database so that you keep it for a long time, or it's data, in which case it should go in the database itself. But having megabytes of session data seems odd.
Thing, right? So, like you said, he keeps flipping pages and keeps seeing the same stuff over and over again. And so if you cache that sort of in a session.
But that's a cache, that's not session data.
Yeah, okay. But,
so use memcache, use its own hashing, set up lots of servers if you need it. That's an easy problem to solve. If it's cache data, that's easy. If it's actual session data that's specific to the user and that you sort of have to keep in order for the user session to continue working correctly, that's usually not megabytes of data. That's 100 kilobytes at most in most applications. Yeah.
Question slightly off topic is scaling the backup stuff like the LVM that you're
yeah.
talking about. I currently use the LVM backups. So when you do a snapshot, it's only one logical volume. So if you added another logical volume for some reason, you didn't want to just grow the current one you have, and then through your InnoDB table spaces you have, let's say one data file and your log files on one logical
gotcha.
volume, a data file on another logical volume.
Don't do that. Yeah, so so the question is basically if you have multiple logical volumes in LVM, what do you do basically to take backups? And the answer, I guess, the short answer is if you depend on LVM snapshots for backups, you have to have a single volume to make it work right. Not only do you have to, your logs and data have to be on the same volume to take snapshots.
I was wondering if you do I currently do like flush table with read locks before I do it anymore just with the master.
Mm-hmm.
But if you did a flush table with read locks, and while you're holding that lock, the snapshot of one, then the snapshot of the other, it still wouldn't be considered.
No, so flush tables with read lock blocks commit, but it doesn't stop all activity in InnoDB. So it keeps new things from being written, but the InnoDB is always doing stuff in the background. So you can't trust that flush tables with read lock actually stops all activity, which means you can't trust it to allow you to atomically snapshot 2 volumes. You can snapshot one volume because InnoDB can always be, so for instance, if you have a power supply failure and the machine just goes down suddenly, when InnoDB comes back up, it will do its automatic recovery and it will be in a consistent state. The same thing is true for snapshots. When you take a snapshot, it's the same as sort of cutting the power. You have the data from a very specific point in time, but it's atomic. Anything that was written to the volume, you have in the snapshot. Anything that wasn't, you don't, across all files, across everything. So since you have an exact point in time of everything, InnoDB will treat it as though it was just a failure, and it will recover that snapshot, and everything will be happy. The only thing flush tables with read lock buys you is the ability to synchronize the binary log positions with that snapshot. So flush tables with read lock blocks commit, keeps the binary log positions from moving so that you can do show master status or show slave status, and then take the snapshot. In that time between when you run the command and take the snapshot, nothing has changed.
Can MySQL do transaction log replication?
No. No, it doesn't do transaction log replication. MySQL replication currently is statement-based asynchronous replication. So it replicates the actual SQL statements across. MySQL 5.1 has what's in the manual called row-based replication or change-based replication, which replicates things based on images of the rows themselves. But that's still not transaction log replication. It's just replicating the logical change rather than the logical command. Other questions?